I'm going to tell you something about the half-of-century studies of cosmic rays in Lodz. And this time when I have been in Lodz, now I am outside in different universities. I would like to show you this picture. This is the St. Katarina Church in Gdańsk, it's not in Lodz. And this is the first pulsar clock built here, the 16 antenna. The accuracy, they use the signal from 6 pulsars to correct the time. And the accuracy of the measurement of this time is 10 times higher than the accuracy in the atomic clock. But I will not so precise of this clock. So you see this antenna. That was a nice thing because this antenna was built 20 meters above the trunk of the well-known Polish astronomer Hevelius. This church, in fact, was the Hevelius church. So let me start with this first experiment, a large experiment connected with the name of Professor Zawadzki. And as you see, this is the sentence which I heard from my teachers, that Zawadzki discovered in the density spectrum of extensible showers. And this is the copy of the from Handbuch der Physik of the Kakani paper. You see the point which Zawadzki got here with the changing of the slope of the gamma is just the slope of the spectrum. When you look on densities, then the density is important for this measurement. This is the densities in the central. This is the rapidity distribution, the density of particles, and so more or less 100 particles per square meter are connected with shower around 5, 10 to 15 particles. But I think that the real need, to be honest, was found by well-known colleague of Christiansen. The paper was published in 1959, but I would like to put here the sentence, which is possible to find in the introduction. The sentence connected with well-known Zaczepny, Christiansen and Chudakov, well-known Russian cosmic ray physicist. But why I put this sentence? This is the first sentence I know when people correlate the changings in the cosmic rays extensible showers with the interaction properties of ultra-high energies. In whole of my life, everything was in between. So either we prove that it must be something different than we expect in the high-energy interactions, or we try to change the primary composition. The game is simple. If you keep the scaling, so-called Feynman scaling, usually go to very heavy composition. And in my life, everything started with this picture. This is the production of pions in the interaction of primary proton with emulsion with Ilford emulsion. So what I should say, these things show the first that there are two cones, the forward and backward cones, and this important cones for us in extensible shower business is somewhere here. You can find that the angle is 0.003 radian. And I would like to say one sentence about the situation of which we had in Lodz. We have been between Krakow and Warsaw. In Krakow there was Professor Mięsowicz and Niewodniczański. Mięsowicz built the first balloon. If anyone interested about stamps, then there was a stamp, a star of Poland, which you will find is between Polish stamps. It is 1938. This balloon was built, and unfortunately there was the accident, and the balloon didn't start. I'm talking about 1937. The copy didn't start because there was the Second World War. Just to show you a real thing, I should show this. This is just a knee detected by Christiansen. You see 285 hours of operation and 490 showers. When I have been in Cascade, as the member of Cascade, we got this shape after 1 week of data. Thank you. The real paper which I found, the first paper which I found is this paper published in 1954 about cosmic radiation. Zawadzki came back to Poland from Paris in 1947. The first lecture which he gave lecture in 1948. And this is the extended version of this lecture about cosmos. We built the Geiger-Miller counters. It was not difficult to build Geiger-Miller, but it was difficult to build cheap Geiger-Miller counters. So to do the cosmic rays, we need a number of these Geiger-Miller counters. And let me show you only acknowledgements which tell you who was cooperated in this business. France, Amsterdam, and University of Manchester. I have a few pictures at that time when I started to be the member of this group. Professor Zawadzki is this guy here, around the technicians. He's going to explain cosmic rays to them. Everything started Zawadzki together with Hofmocker and together with Firkowski. There was 3 people at the beginning involved in the cosmic ray study. When Zawadzki decided to go out from Poland for Constant to Paris, and after 1968 we had a political problem. There was more than 20 years in our group. This guy here is Tomaszewski. He started the Martian chamber business with Russian colleagues, so-called Pamir experiment. About the Martians, from the Warsaw we had a strong group. As we hear, it's not easy to get Nobel Prize, but Janusz and Pniewski, they have been nominated to the Nobel Prize for the hyper-neutron physics, which they arrived at the election. I would like to show something very small but connected with me, sorry for that. When we, in our life, there was commonly used parameter, so-called H parameter, to describe the electron distribution. And everyone following the Greiser and the Kochoni used the S equal 1.25. And I noticed that when we selected a group of showers, that we noticed that this average is not 1.25 but 1.14. And it was clear. I did a Monte Carlo for the full device. And I noticed that in this detector, which was far away, it's impossible to get agreement if you assume that this parameter is 1.25. Our power, which we have, because we have a lot of collaborations with Verrier since 1958, with University of Durham, with Professor Arnold Wolfenberg, which is here from 1965, and with Moscow State University. I'm happy to see my colleague from Moscow, as well as with Forschung Center of Karlsruhe. By the way, I will not speak much more about collaboration between Moscow State University, since the next speaker will probably follow this. So what we got cascaded, there's something which is much better than we have from Lodz experiment. Electrons measured with very big accuracy. As you see here, these shapes are steeper than this 1.25. Muons with two different thresholds of energy, hadrons with energy higher than 50 GeV. So this is a beautiful experimental material. Before I started to prepare this talk, the question was, what is the most important discovery in Łódź? And I think that this is a gradient. Prof and Wolf from there, they found the gradient of cosmic rays in the galaxy, which means that everything which we measure, or mostly what we measure, came from our own galaxy. And you see the different things, anisotropy of heavy nuclei, anisotropy of gamma rays, everything. It's not all, right? I didn't put all papers, but there is a number of papers. They analyzed the harmonic amplitude of the anisotropy, and let me put your attention that they got the noise. It means that this isotropic distribution. And this is the north and south part of the sky. So there is a very interesting region around 10 to 8 where there is also almost no anisotropy. And the next is the dependence of the galactic altitude enhancement factor. I put the definition of this factor. And also, everything here is clearly from the galaxy, from our own galaxy, but in the region between 10 to 19, 10 to 20, it's also clear that something is not from our galaxy. The experimental data are from Havera Park. I'm happy to see Watson with us, and from Sydney. So it was clear that this very high energy showers, they do not come from our galaxy. This you have seen. And let me put your attention that this question is still on, and a year ago, the Elkin and Wolfman, they published again the paper about the radio gradient of cosmic rays in our galaxy. The second discovery was discovery of the Newport showers, and you see the list of part of papers which we published. And people use up to now the Newport showers to estimate the flux of gamma rays. It was nice for me to notice that in the next European conference in Moscow, which will be papered by Fomin Kulikov from the old Moscow State Device about the Newport showers. So this question is still on. The next, I would like to point out that there was the first observation of the extensive shower from particular source. We got the signal from Kempa. And the quality of the signal you may see here. After us, in several experiments, people also quoted that they observed small signals from Kempa. But more important and more known is the work done in Kiel, where they found the enhancement from the direction of signals like tree, and so on and so on. So this is what we started in Lodz. People continue. About the primary mass composition, let me show you the first paper about the bump around 10 to 15. Which was published in '74, and this is the structure of primary spectrum. Partly the bump we built because we used the conversion factor between energy and shower size. And the next proposition of this bump, you see here that you have the two galactic origin sources, the one which slowly died, and we heard about this, and the second, which is also galactic and proton-rich in in our case. I got a nice results which we published in '88 from the Kiel experiment. Using the fractal analysis, I divided showers into two groups, proton-like showers and heavy-like showers. And clearly you see that for higher energy, for higher sizes, we almost exactly we have this light showers, or showers produced by light nuclei. By light I mean protons and alpha particles. That's all what was possible to say after this study of the fractal structure of the core of the shower. And that's also from Cascade we got that when you look at the number of hadrons versus the number of electrons, so the good fit you will get, assuming that you have proton showers. The calculations from Corsica. So, but the question is still on. I mean, it's not easy to say what is in fact in this region of higher energies, because you see the idea about bump from the Lindsley paper, which is later on, published later on, almost 10 years after our paper, but it's clearly unknown, this iron group of particles. But when you look today on this problem, so you know this picture probably, there are different group of nuclei and the spectra multiplied by e to 2.5, so this spectra are quite powerful. And I would, let me put let's concentrate please that in 1983 we suggested the so-called constant mass composition model, assuming that the composition don't change in this region. So I think we still are close to this idea. And a well-known picture which describes the primary particles. Due to this idea presented in 1989 by Dr. and Wolfenday, we have two galactic sources and one extragalactic. How it looks now. When you look on these papers now, then you will easily find that people still plot their spectra from supernovas and then this part from AGNS. About hydrogen interaction model, maybe I will not go too far because I have no time. But I will just, let me show you the idea of which Alparelli wrote in his book. The Dutch Wolfenday put forward an elegant way to link such violation with the well-established violation. It's replace the Feynman x by the Feynman x multiplied by the ratio of energies to this power of alpha. So physics, in fact, in the Dutch and Wolfenday model is here, and this alpha value of this particle, of this parameter. So what is the situation now? When you on the left part, you have data about the particles, such particles producing interactions shifted by this logarithm through alpha square that's over m. So this was the idea of Dopchik and Wolfenday scaling. But when we look into the data which we have now, it's much more difficult, even now from LHC, assuming that we will have better data. It's very difficult to decide what is the model of high-energy interaction. Just to show you the comparison between Dopchik and Wolfenday fit and the pi plus particles produced with different models which we have in Corsica. For pi pluses and for pi minuses. And as you see, the fit is very good. And the data which we the first comparison with the new LHC data here. If you take the models which are in Corsica, we may say that most probably Sibyl is the closest model to Poland, this data. But you wait on the data which we will have from 14 TeV, so this point will decide that in fact which one model is true. Ehrlichen and Wolfen, they wrote in Cernku years ago that seems to be that this data shows that alpha particles should be 1.11 and very well fit the experimental data. And the last things which I would like to say, if Chairman will allow me, is about the study which we did with our Russian colleagues at Pamir. This is the device which is a Martian calorimeter with lead and films, and so on and so on and so on. And then such calorimeter waits 1 year, and we took the films. What we measure, you see here, we really measure the core of extensive showers. Well, this is the picture of real films. There are two emulsions from two sides, so we reject one emulsion from one side, and you see this is something which we call family globes. If the value of this black part in the center is higher than 5 millimeter, we call this that we have the family with halo. I think we know the energy quite well. Years ago we did the Monte Carlo using GM4, and so I think that the estimation of the energy of all of these drops is reasonable. I would like to show you the particular case. We call this quasi-model. First layer, second layer, third layer, fourth, fifth, sixth, seventh, and eighth. Just like a quasi-model. We have a problem with this energy in families, and several models we try to use. And looking on the last data from LHCF, I still do not believe that we will describe this energy spectra using this data at the moment. But I would like to correlate two things. You know, quite a long time ago I made this plot. What is here? This is the integral spectrum of showers from the sun experiment. The showers are divided due to the H parameter. I said you a few words about this parameter. So the first group of showers is here. The second, which S parameter between 0.35 and 0.75, they are so-called very young showers. And the intensity of these very young showers fits very well with the intensity of gamma ray families, without halo. When I look on the point, when I'm thinking about so-called very old showers, then I got a very nice agreement between these showers with this H parameter and the intensity of these gamma rays with the halo. But less young, it means that the proton interacting deeply in the atmosphere. This old, oh, that's a question. Because either it is iron or something else. Why we observe such old showers at the mountain altitude? And in JC collaborations, there was a Polish group from Krakow of Henryk Wilczyński, and I have 3 examples of interactions. JC, this balloon experiment, And they found 3 such interactions of proton, neutron, and proton with the motion. Then all particles in the forward directions, they are photons or electrons. There is a terrible asymmetry. All hadrons are going into the back directions. All photons or electrons, they go in the forward direction. So you see 3 such examples. I'm going to the end. So at the end, let me come back to the story of the neutral showers. Soon after the neutral showers was discovered, and we estimate and correlate this neutral showers with gamma primaries, Mars, Dodczyk, and Wolfer, and Zawadzki, they published the paper that not everything is in agreement when we assume that we have gamma rays really, and they produce these neutral showers. And the idea was that maybe there is something else. Where something else, as you see, even we authors believe that maybe there is a particle which the long lifetime will branch into electrons. So I think that this question is still on. Maybe there is really something in the interaction. Thank you very much.